Intervening material has two levels. It was nonsense syllables or it was numbers. And because it only has two levels, we can just inspect the means. We spoke about this last week in the context of gender. So if we inspect the means, let's grab my data. Let's actually look at something that's labeled. Here we go, numbers pairs versus nonsense syllables. So number pairs, so these first three, we see 12, 3.5, and 15. For nonsense syllables, it's 5.8, 10, and 13.5. Now, if I really want to compare these and go, what's going on, I could quite simply use the tab stat again, but rather than by cell, I would simply say by intmat. And now I can see that the mean retention number of syllable pairs remembered, if you had number pairs as your intervening material, was 13. So people who saw number pairs, on average, could remember about 13.5 syllable pairs. If you saw nonsense syllables as the intervening material, you could only remember 9.3. So averaging across repetition, being exposed to number pairs did not hamper your memory of syllable pairs as much as if you were exposed to nonsense syllables as intervening material. And that's averaged across repetition. Now, if I go back up to my ANOVA, we also saw that the number of repetitions was also significant. So again, I can grab these means by switching out intmat for number. Oh. And here I can see that 4 times repetition, 8.91, 8.92, 8 times is 11.75, and for 12 it's 14.33. It's going up. But because I have more than 2 degrees of freedom, I can't just interpret this on its own. I'd have to go and do my contrast testing like we did back in week 6. Then we get to the interaction. For the interaction, to make sense of that, I could look at these 6 means and go, okay, so what's going on? But again, just like with the number of repetitions, because I've got more than 1 degree of freedom, because I'm comparing more than 2 groups, I'm going to have to look at contrast testing. Now, today, despite the fact that technically there are hypotheses, I want to pretend like there isn't. And so we're going to talk about 2 different approaches to post hoc contrast testing. So, 2 approaches to post hoc contrast testing. The first is an optimistic approach, and I guess the idea of both of these approaches is if you're going down the route of post hoc, you're going to be using either a Tukey's or a Sheffe correction adjustment. And in both of those cases, you're going to be punished on the assumption that you're looking at everything. So these approaches were developed under that assumption of, well, why not test everything? You know, if you're going to be punished for it, why not do it? But I guess the technicality that comes with this, particularly if, say, you are under time pressure, is that you might not have the time to run everything. So these 2 approaches to post hoc testing are designed to test everything without literally testing everything. And they do this by finding the smallest pairwise difference that is significant. In which case you can say, well, if the difference is larger than this critical threshold, then everything is significant. Everything above that is significant. So the optimistic approach, if we're going to be an optimist, we would say that even my smallest difference will be significant. Everything is significant. Everything worked. Even my smallest difference will be significant. So the optimist would actually say, okay, so if the smallest difference is significant, then all other differences are also significant, because every other difference must be larger than my smallest. If my smallest difference is non-significant, then as the optimist, well, maybe my next smallest will be. And so then I will test the next smallest, so slightly larger, but the next smallest, the next closest to being smallest, test that difference. If that's non-significant, I move to the next, and I move to the next and the next until I find significance. Once I find a difference that is significant, then I can say, well, everything larger than this must be significant. Everything small is non-significant, and everything that is a difference equal to this or higher is also significant. On the other hand, we have the pessimist. The pessimist goes, well, everything is broken, nothing worked, even my largest difference is non-significant. So the pessimist will start at their largest difference, and they will test whether or not that pairwise difference is significant. If it's non-significant, then every other difference must also be non-significant. If your largest difference is not a significant difference, then anything smaller can't be significant. If the largest difference is significant, the pessimist will move to the next largest and continue working down until they reach non-significance. And then they can say, well, anything of this difference or smaller is non-significant. Anything larger is significant. Now, regardless of which approach you take, they'll arrive at the same definition of the smallest difference that is significant. So the decision as to whether or not you should be an optimist or pessimist, in my opinion, should bank on two things. One, are you actually an optimist or a pessimist? But two, what's the most quickest outcome? Sometimes you won't know. Maybe by looking at the data, you can go, well, the smallest difference is massive, so let's start there. Or maybe you go, well, the biggest difference is actually tiny. So you can use that as a guide. My rule of thumb. This is all about time and time management. So I actually want to do this so I can actually show you why this logic works. So I want to be an optimist because I personally am an optimist. Everything always works, and when it doesn't, it's obviously because it wasn't meant to. So we need the means and standard deviations. I know we've already grabbed these, but let's just do it again. And we're doing this for intervening material. Not for intervening material, sorry, we're doing this for number of repetitions. We don't need to do it for intervening material. So we've got our means for the number of repetitions. So we now need to start doing some hand calculations. So what I've done is I've created up the top here what I call my contrast table. Now all this table has in it is my different groups for 4 times repetitions, 8 times repetitions, 12 times repetitions. And then underneath that, I've put their means. So 4 times repetition had a mean of 8.92. For 8 times repetitions, it was 11.75. And for 12, it was 14.33. Okay. You can do it to 2 decimal places. Do it to however many decimal places you need to do it to. Often more is better. I've got 2 here for now. And then underneath, I've got contrast 1, contrast 2, and contrast 3. These are the 3 contrasts that I could be running if I'm going to run all of them. And I know that there are 3 because if I'm using the optimistic or the pessimistic approach, these are pairwise contrasts, which means I'm only ever comparing 2 means together. And if I've got 3 means, I can compare 4 to 8, so that's 1 contrast. 4 to 12, that would be a second contrast. And then 8 to 12, that would be a third contrast. So there are 3 contrasts I could run. So, I'm an optimist. I want to know what's the smallest difference and test that first. So over here, I've got my 3 possible contrasts, 4 versus 8, 4 versus 12, 8 versus 12. And all I've done is I've calculated the differences. Now, if you're using Excel like I have, I've literally gone in and I've gone the bigger mean minus the smaller mean and let Excel do the hard work for me. And what we find is that the smallest difference is between 8 and 12. Okay, so now that I know that, contrast 1 needs to compare 8 to 12. So what on earth are these numbers here? These here are my contrast weights that actually are going to inform my mathematics and my contrast to say compare 8 to 12. So there are some rules here. First of all, I use 0 to get rid of groups that I'm not interested in. So in this first contrast, I only care about 8 and 12, so I give 4 0. And then I need to assign a -1 and a 1 to 8 and 12. I could assign a 1 to 8 and a -1 to 12. I can assign -1 to 8 and 1 to 12. It doesn't matter. But one needs to be negative, one needs to be positive. They don't even need to be 1s. I could use 0.5s, I could use 2s, I could use 10s, I could use a million if I wanted to make this hard. But the rule of thumb is that whatever you use, they need to all add up to 0. So all I've done is just put in a formula here that adds up all of my contrast weights. So my 0, my -1, and my 1, I can see they sum to 0. If I use -0.5 and 0.5, that sums to 0 as well. I couldn't use 5 here because that would sum to 4.5. That wouldn't sum to 0. So whatever weights I do use, they need to sum to 0. My recommendation is to stick with 1s. 1s are easy to interpret. And if you stay at Macquarie and you move on to our third year stats course, using 1s and 0.5s have very strategic timing. So you strategically use 0.5 or you use 1. So I recommend just getting used to using 1 here. It'll make your life easier later on. My next smallest difference would be 4 and 8. So I would have -1, 1, 0. And then my largest difference is 4 and 12. So I'd have -1, 0, 1. So the reason why I'm giving 4 -1 and I'm giving 8 -1 is not because these are just the first number. It's actually because these have the smallest mean. And the reason for this is in our first step, we're actually going to go this number, our positive numbers, minus our negative numbers. And if you put the smaller means on your negative number, you'll always get a positive value coming out in the first step. And this is not super important. It actually doesn't matter. In the second step, we do something to make these absolute values anyway. But doing it at this point just helps. For whatever reason, as human beings, we don't handle negative numbers very well, even though they're exactly the same. So ensuring that you get a positive number coming out is just a safeguard for yourself. Okay. So now that we've decided what these weights are, what on earth do we do with them? These are going to tell us what we're comparing and how to compare them, but how do we actually compare? Well, we start off by calculating what's called a contrast value. And unfortunately, the cheat explanation of this is it's just the differences that we calculated here. But there is a formal process, and it's this nasty looking equation here. So let me walk you through what this is. This little symbol here is a psi symbol, but in the context of contrast testing, it just means contrast 1. So psi 1, contrast 1, equals W1 times X bar 1. W is a contrast weight, and X bar is a mean. So take the weight of variable 1 and multiply it by the mean of variable 1, or level 1. So here what that's going to be is the weight of 1. 1 is going to be our 4 times, that's 0, and multiply it by 8.92. For those of you that are mathematically inclined, you'll already be able to go, oh, I see why he gave a 0 there. Because once I multiply 0 by 8.92, this will equal 0. So if you remember before, I said we assign 0 to things we want to get rid of, because in this first step, it will literally get rid of them out of the equation. And then W2 will be -1, X bar 2, 11.75, W3, 1, X bar 3, 14.33. So all I'm doing is assigning my contrast weights and then in brackets the mean for that group. So then this is what the equation would look like if I wrote it out in full. 0 and 8.92, -1 and 11.75, +1 and 14.33. If I multiply my 0 by my 8.92, multiply my -1 by 11.75, and multiply my 1 by 14.33, I get 14.33 positive minus 11.75, and this solves to 2.58. So this is just the difference here. This is just a really complicated way of going 14.33 minus 11.75. But this is important because we can do much more complicated contrasts that aren't just two means, and then it's not so straightforward to just take the difference. You actually need to follow this process. So now that we've got our contrast weight, we need to calculate our sums of squares for the contrast. So now we have sums of squares for contrast 1, and the formula gets really nasty. So we have a fraction. The top half of the fraction says A times N times the square of contrast 1. And then underneath, we have the sum of sign, so this E just means the sum of W squared. And I'll show you what this looks like in a second. So we already know that W represents our weights. And we already know that this sign here represents the contrast value, or the contrast itself. So we know that psi 1 equals 2.58. The A symbol represents the number of levels on the other IV. So we're looking at repetition, and repetition has 3 levels. If we recall, number pair, intervening material was our other variable, and it has 2 levels. So our A here is going to equal 2. N represents the number of people in each level. Now, in each one of these levels, if I go back up to our original data, our little n equals 6. So, if we break all this down, A is the number of levels of my other variable. N is the number of people per group. Then I have my contrast weight squared, and then the sum of each of my contrast values squared up the top there, and the sum of my contrast weights squared. So why am I going A times N? What's the point of this? Well, if I go down here, A is 2 and N is 6, and 2 times 6 would give me 12. Now, if I look at how many people were in each of my repetition groups, I can see it's 12. So by multiplying my number of people per cell by the number of levels of my other IV, I'm actually just recreating the size of participants, the number of participants per level of just this IV that I'm interested in. So that's all this is. Really, if you want to, you could simply say it's the number of people per group for the IV that you're testing, which in this case would be 12. But the technical formula is A by N. So if we write it all out, we get 2 for A, N for 6, 2.58 squared, because that's what our contrast value was. And then what this sum of formula looks like would be 0 squared, because that's our first weight, plus -1 squared, that's our second weight, plus 1 squared. So each contrast weight is squared. Now, there is a purpose for squaring these together before we add them up. 2.58 gets squared because then if it was -2.58 or if it was 2.58, it's going to produce the same positive value anyway. So if you remember before, I said it doesn't matter whether or not you assign a -1 or a 1 to 8 and 12, because in the second step we get rid of this. And that's what this square function is doing. It's getting rid of the negative sign. Because we're squaring this, we also have to square our weights, but squaring our weights also gets rid of negative signs again. So you don't have to put brackets around each of these. I personally put brackets around them to remind myself that I need to square each of them individually before I add them up. If I add them up and square them, they'll always sum to 0 because that's what they need to do, and you can't square 0. 0 squared is just 0. So then I go 2 times 6 gives me 12, and I've left everything else the same. And the next step of the equation, I go 2.58 squared. And then I go these two multiplied by each other, which gives me 79.8767. You can see I'm starting to use larger decimal places here. And then underneath, if I square out these numbers, I get 1 plus 1, which gives me 2. And 79.8 and a bit divided by 2 gives me 39 and a bit, almost 40. So the sums of squares for my contrast is 39.9384. So this is a really long process and it looks really scary. I get that. My recommendation is to do this as many times as possible and then use that as a way to practice and get comfortable. Because once you do this a couple of times, it actually is really straightforward. Once I've got this, I then need to calculate my f. So I take my sums of squares and I divide it by my mean sums of squares error. Now this is an interesting point. If I go back to the ANOVA, I've been telling you week in and week out now that to calculate an f, you take the mean sums of squares for a particular variable and you divide it by the mean sums of squares residual. Now what we're doing is we're taking the sums of squares and we're dividing it by mean sums of squares residual. Now, we're not doing this because it's an error. We're actually doing this because in a contrast, there's only ever one degree of freedom. So the reason for this is we have negative numbers and positive numbers. And even if we were comparing multiple means, because they always have to sum to 0, you always end up having a negative group and a positive group, a negative number and a positive number. So you always have a degree of freedom of 1. And intervening material is an excellent example of when you have a degree of freedom of 1, your sums of squares will always equal your mean sums of squares, because 121 divided by 1 is just 121. So by using sums of squares here as our numerator for our f equation, we are technically using the mean sums of squares. We just don't have to calculate it. The mean sums of squares error comes from our omnibus test. And as we said just a second ago, and I'll bring it up, and the mean sums of squares from our omnibus test is 2.92. So this equation then becomes 39.9384 divided by 2.92, and that gives me an f of 13.68. So this is my obtained f. This is the equivalent of this f here. So how do I know if that's significant? How do I know if 13.68 is a significant f? And how do I adjust for multiple comparisons? Well, we need to calculate a critical f, and this is the f that we would get, the largest f that we would get if the null hypothesis was true. So in other words, the f that we would get at effectively 0.051. Or if our p-value equals 0.051. So any f larger than this critical f has to be significant. And we're going to calculate a Sheff critical f because we want a Sheff correction. And so to do this, we need to find what our critical f would be normally for our ANOVA and multiply by the degrees of freedom for the IV. So we already know that the degrees of freedom for repetition is 2 because we have 3 levels. 3 minus 1 is 2. So now we need to go find our critical f, for the main effect of repetition and multiply it by 2. To do this, we need an f table. Here is one I prepared earlier. This is actually from the textbook that I used when I did this course. You can even see my little sticky tabs and my own writing through this. That's my handwriting to remind myself of what everything was. Now, we need 2 numbers. We need the degrees of freedom for the numerator, which is the degrees of freedom for our IV, and the degrees of freedom for the denominator, which is the residuals degrees of freedom. So let's go back to our ANOVA table to remind us what these numbers are. We're looking at number of repetitions. The degree of freedom is 2, and then our residual is 30. So we want the f for 2 and 30. So let's zoom in so that you guys can see this. So I go to 2, this is my degrees of freedom for my IV, and then I go down to 30 on this chart, which is here. 2 and 30 gives me a critical f of 3.32. So I would then go back and put in 3.32. My Sheff f is 3.32 times 2. If we do the math, that gives me a Sheff critical f of 6.64. My obtained F was 13.68 and is much, much larger than 6.64, suggesting that my smallest difference, my difference of 2.58 units, is a significant difference. So in other words, the difference in the number of syllable pairs recalled between 8 times repetition and 12 times repetition, averaged across intervening material, is a significant difference. And because this is the smallest difference, then my next smallest difference of 2.83 must also be significant. If I just took a second now to actually do that, we would get a contrast value here of 2.83 instead of 2.58. All of this math would effectively stay the same, except this would now be a larger number. This would be 2.83. And 2.83 squared is going to give me a number larger than 6.652, which means when it's multiplied by 12, it'll give me a larger number here again. So when it's divided by 2, I'll have a larger sums of squares. A larger sums of squares in this formula, the denominator won't change. It's actually going to produce a larger f. So my f is only going to get bigger with a bigger difference, which is why I know if this f is significant, every difference larger than 2.52, was it 2.58, must also be significant because my obtained f will only get larger. Okay, so that's kind of interesting. And we can conclude on that exactly the same way as before. Only now when we say we have a f on 0.05 and on so many degrees of freedom, we would also say when compared to a critical chef AF of 6.64. So we're no longer citing p-values, we're going to compare our obtained f to the critical f in our conclusion. Otherwise, it's exactly the same. So the real-world conclusion then might look a little bit like this. And you can see I'm shifting back to the real-world conclusions. Just because the last couple of weeks have been doing that more journal style, this week I want to go back to the real world. And it might look something like this. In the population, the mean number of nonsense syllable pairs recalled is higher for those in the 12 repetition condition compared to both of the 8 and the 4 times repetition, when we average across the intervening material. Moreover, the mean number of nonsense syllable pairs recalled is higher for those at 8 repetitions compared to 4. So because our smallest difference is significant, we're saying that all of our pairs are different. And you could include your obtained and your critical Fs in there if you wanted to as well, and I would recommend it.